All right, this is a review of Chapter 8 and 9, bonding. Make sure you got a paper and pencil out in front of you, a place to write stuff down, and a book. Pause the video now to make sure you have those. Bonding. Two separate entities you've got to keep straight in your head. Bonded things that contain a metal, called ionic. Bonded things that contain only nonmetals. Notice only nonmetals right here. These are called molecular or covalent substances. Words are used interchangeably. You got to know them both. These are the things that have Lewis electron dot structures formed. These things do not. These things are held together by covalent bonds. These things are held together by ionic bonds. You can use dashes to illustrate them, metal and a nonmetal, but you don't go putting dots around them that much. I mean, you could here, but you don't have complete octets and stuff like that. Ionic bonds are held together by something called lattice energy. Lattice energy is proportional to Q1 times Q2 divided by D, where Q1 and Q2 are the charges on the ions. The bigger the charges, the bigger the lattice energy. They're inversely proportional to the distance between the ions. Smaller the distance, the stronger they're held together. Covalently bonded things, well, they depend on what are called bond enthalpies. And the general rule of thumb is the more bonds, the more energy. Carbon-carbon single bond, less energy than a carbon-carbon double bond. Less energy than a carbon-carbon triple bond. And every bond has a different enthalpy. Keep those two areas straight in your mind. When you mix them up, bad things happen. These guys, molecular compounds right here, we're going to spend almost all the time on. We're going to talk about how to draw Lewis dot structures. We're going to talk about how to determine what kind of bonds are in between them, whether they're single, double, or triple bonds. We're going to talk about paired and unpaired electrons. We're going to talk about the strength of those bonds. We're going to talk about the length of those bonds. We're going to talk a little bit about what kind of shapes the molecules undertake, whether there is a certain type of bonding that is hybridized called sp or sp2 or sp3. And we're also going to talk about whether they're called sigma or pi bonds. All this stuff fits only with nonmetals. It doesn't fit over here. We don't talk much about this, but some kind of questions show up on the AP exam. Then lastly, we'll take a look at a few AP exam questions, and mostly they focus on this stuff for right now. We'll find out that these are the things right here that undergo those intermolecular forces. Those intermolecular forces like London dispersion forces, dipole-dipole forces, hydrogen bonding. These guys do not. The only thing that they decides what they do is the lattice energy of these guys. Have some more paper. Here we go. Let's talk about covalent or molecularly bonded things. Step number one, you got to be able to know how to draw Lewis electron dot structures. And the step-by-step on drawing Lewis dot structures is outlined for you on page 310 of the 10th edition of Brown-LeMay Burston. So right here, Lewis dot structures right here. Okay, they go through the step-by-step. If it doesn't work, try multiple bonds right here. Single bonds, double bonds, triple bonds. Then they talk about electronegativity and bond polarity. Remember that polarity is symbolized by these little Greek letter deltas. You could zoom in on that. You can see that this is a positive delta and this is a negative, meaning there's a partial negative charge here, partial positive charge here. Remember those for bond polarity. Okay? After you can draw the Lewis dot structure and determine the polar nature of the bond, okay, is it polar or not? Then you can go on and you can actually decide if it's an appropriate Lewis dot structure by looking at something called formal charge. Now, there hasn't been a formal charge question on the AP exam for a while, but there was one a couple of years ago, but it wasn't that big a deal. We can zoom through that if we encounter a Lewis dot structure that's got it. Then occasionally you end up with these things called resonance structures, where bonds that are single and double actually pair, and then it turns out to be like a bond and a half at each spot, rather than a double bond at one and a single bond at another. Then there are all these exceptions to what's known as the octet rule. There are more electrons, less electrons, and odd number of electrons occasionally. And lastly, we talk about strength of these bonds as well. So let's do a couple of examples of Lewis electron dot structures where something like this might happen with a bunch of weird things, because those are the ones that everybody wants to know about. Let's first of all look at drawing the Lewis electron dot structure for nitrate, NO3 minus, okay? First thing to do, sum the valence electrons. 5 for nitrogen, 6 for oxygen, times 3 plus 1 because it's got a charge of -1 right here. If you don't have a periodic table in front of you, you probably want to get one, because you'll want to use the periodic table to help you determine the number of valence electrons in a compound. So for example, right here, I knew that nitrogen had 5 valence electrons because it was in group 15. I knew that oxygen had 6, and fluorine would have 7, and any of these noble gas guys would have 8. Carbon, this group would have 4. These are about the only ones you're ever going to see when you're drawing those Lewis electron dot structures. You should just know those by their groups or families. Total number of valence electrons then, 18 plus 1 is 19, plus 5 is 24. So 24 total valence electrons. Take the least electronegative atom and stick it in the middle. Take the least electron. Remember, electronegativity increases up and to the right. So between nitrogen and oxygen, I choose nitrogen and stick it to the middle. Bond everything else around it. That uses up 2, 4, 6 electrons. 24 minus 6 leaves me with 18 valence electrons. Now, if I go ahead and I try to put my electrons around it, it's not going to work. 2, 4, 6, 8, 10, 12, 14, 16, 18. Nitrogen electron deficient, not going to work. Can't do that. So try a double bond. Okay. 2, 4, 6, 8 used. 24 minus 8 leaves me with 16 remaining. 2, 4, 6, 8, 10, 12, 14, 16, 18. Didn't need those on the nitrogen, sorry, because I had 2, 4, 6, 8 electrons around nitrogen already. Okay, there is my nitrate. Remember, when you write the Lewis electron dot structure of an ion, always put it into brackets and then put the little charge right outside the bracket. Now I've got a problem. Notice how the double bond is right here between this nitrogen and this oxygen. What happens if the double bond was here? Or what happens if the double bond was here? And as a matter of fact, the double bond tends to switch between these areas, and it's said to resonate between these areas. And so instead of having a double bond here and a single here, or a single here and a double here, I actually have a bond and a third, length and strength at each one of these spots. A bond and a third. Now, from this, I should be able to determine what's known as the shape of the molecule. The shapes of the molecules are actually in Chapter 19, and we'll come back to that in just a second. Let's talk a couple other odd Lewis electron dot structures. Odd Lewis electron dot structures, and then odd exceptions to Lewis electron dot structures, and then we'll come back and look at shapes of this guy and other ones in just a second, okay? Let's take a look at one that's easily confused, HClO, okay? This is known as hypochlorous acid. Now, a lot of people think that, okay, I'm going to end up with the H connected to the Cl connected to the O. No, 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 no. In oxy acids, it never works out that way. It's an oxy acid because the O is connected to an H, and it turns out to have this shape right here, so the hydrogen can be cleaved off of there. Looks like an odd exception because it's usually written this way with the H, and then there's HClO2, and then there's HClO3, and people think the H is stuck to the Cl. It's not. You can replace this Cl with Br. You can replace this Br with an I, and now all of a sudden you have all of those oxy acids figured out and knowing that the H is stuck to the O. Odd exceptions. More odd exceptions, okay? Let's look at nitrogen monoxide, odd exceptions. Okay. Nitrogen, 5 electrons, oxygen, 6. Oh, it's 11 electrons. Yup. Ends up looking like this. 2, 4, 6, 8, 10, 11. Odd number of electrons. Yeah, it happens sometimes. Rare. Weird. Weird, weird, but it happens. Okay? Another one. BF3, boron trifluoride. Boron, 3 electrons. Fluorine, 7. Times 3, 21, plus 3 is 24. Boron in the middle, least electronegative, stick it to the fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. 24. I counted wrong. That's 24. Anyway, boron, electron deficient. 2, 4, 6 around it. Is that okay? Yes. Boron can be electron deficient. It usually is. It has less than an octet of electrons. Which ones does that happen to? Boron. Pretty much that's it. Boron. You'll see a couple of weird ones. Some people say beryllium can, but that's a metal, so technically not supposed to happen that much. Expanded octets. These happen a lot. PCl5. Okay, phosphorus 5. Chlorine 7 times 5 is 35, plus 5 more 40. Phosphorus in the middle, least electronegative. Bond all the chlorines around it. Works out pretty good. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. 40 electrons. Notice how I put these dashes around here to represent 2 electrons. That's legal on most AP exams. Wait a minute. Phosphorus has 2, 4, 6, 8, 10 electrons. Expanded octet. Can phosphorus have an expanded octet? Here's the rule. If it's third period or below, phosphorus is in the third period or below, it can have an expanded octet. Why? Because it has empty d orbitals. Because remember, this is the 3p sublevel, the 3 ds. Well, those are right here. They're not filled. These guys are the 4p's. Where's the 4p's? Here, not filled. Here's the 5p's. Where's the 5ds? Here, not filled. They have those empty d orbitals that are available to use in bonding. Expanded octets. Those are a bunch of weird ones. Those are ones that cause issues when you have to find the shapes of things. Lastly, let's talk about strengths in Chapter 8. Strengths and lengths of the bonds. And this is on page 328 of your Chapter 8 in Brown-Lemay-Burston. They've got a table right here of average bond enthalpies. Notice they're given in kilojoules per mole, and notice every single number on there is positive. Every single number on there is positive. Why is it positive? Because you need to add energy to the bond to break it. You have to put energy into the bond to break it. You have to put energy into the bond to break it. What do you have to do to break the bond? Put energy in to break it. Now, when something forms a bond, once again, let's say H forms a bond with the Cl, then it releases energy, and that would be the exothermic part. But to break the bond, you got to put energy in. And bond enthalpy depends on the length, and it depends on the number of the bonds. You could look right here, carbon-carbon double bond, 614, carbon-carbon triple bond, 839, carbon-carbon single bond, 348. Okay? The stronger the bond, the shorter the bond. Actually, physically shorter. So, single bond, double bond, triple bond, the strongest and the shortest. Second strongest, second shortest. Weakest bond, longest. Shapes. Chapter 9. Okay? This is what's called the Vesper model, valence shell electron pair repulsion model, page 348 in Brown-Lemay-Burston 10th edition. Okay? Two bonded domains around a central atom, 180-degree bond angle. The electron domain geometry is known as linear. 3 electron domains, trigonal planar. 4 tetrahedral, 5 trigonal bipyramidal, 6 octahedral. This is known as the electron domain geometry. This is what happens when there are those number of electron domains, bonded or not, around the central atom. Now, if you have some non-bonded electron domains mixed with bonded, they actually have a special geometric name. These are the overarching domain geometries for each one. You need to memorize the names. You need to memorize the number of shared and unshared pairs of electrons. Let's look at 2, 3, and 4. 2 shared pairs, 0 non-shared pairs, linear. 3 shared, 0 non-shared, trigonal planar. 2 shared, 1 non-shared, bent. Notice how there's an unshared pair of electron, takes up a little bit extra space, drives this angle right here a little less than 120 degrees. 4 shared, 0 unshared, tetrahedral. 3 shared, 1 non-shared, they call this trigonal pyramidal. 2 shared, 2 not shared, bent. This one, remember, we had a sing-song saying for. Love to be the playboy. Okay? L for linear, T for trigonal planar, bent, tetrahedral, pyramidal, trigonal pyramidal, and bent. Love to be the playboy. Okay? What happens when you have more than 4 electron domains? Well, now we're on this page right here. Beautiful pictures in our book. This is on page 354 of the 10th edition. Five bonded, 0 non-bonded, trigonal bipyramidal. 4 bonded, 1 non-bonded, seesaw. 3 bonded, 2 non-bonded, T-shape. 2 bonded, 3 non-bonded, linear. Ooh, another linear shape. 2 linears. Yep. Down here, 6 bonded, 0 non-bonded, octahedral. 5 bonded, 1 non-bonded, square planar. And then right down here at the bottom, square pyramidal, because it makes a pyramidal shape right down here. And then this is square planar because this is a square in one plane of existence. How do you remember the names of these? T, S, T, L, O, S, S. Test loss. Trigonal bipyramidal, seesaw, T-shaped, linear, octahedral, square pyramidal, square planar. You got to have them memorized. Love to be the playboy, test loss. You can memorize them all. You should be able to figure out the name. And you'll see there's questions where they want you to just regurgitate the name and apply it from where it's at. All right? Shapes, chapter 9. Some memorizing to do. We'll have to quiz them again. Okay? Next, polar molecule versus nonpolar. All right? Now, a polar bond means that there's a difference in electronegativity. Difference in electronegativity between 2 atoms. Polar molecule means that there is an asymmetrical shape of the molecule. Here's some examples right here. Okay? Look at this one. Linear, but asymmetrical, because it's carbon and hydrogen. So it's polar. BF3, nonpolar, because it's totally symmetrical. CCl4, totally symmetrical, nonpolar. NH3, polar, because you've got this unshared pair of electrons here on the top. This guy, CH3Cl, polar, because there's going to be a pull for electrons up here to the chlorine. It's super important that you can tell the difference between polar and nonpolar molecules, because those are the ones that experience different types of intermolecular forces giving rise to different changes in physical properties, whether it be boiling point, melting point, ability to sublime, ability to change phase, and helping it dissolve in water too. Hybrids. Hybrid orbitals, okay? sp, sp2, sp3, sp3d, sp3d2. Hybrid orbitals. Okay? If you have 2 things, for example, BeF, I know Be is a metal, but they use this as an example anyway because it's kind of like a nonmetal. Totally breaks all the rules because there's only 2 shared pairs of electrons right here. Linear, these hybridize. to be sp hybridized orbitals of equal energy. One from the s, one from the p's. Okay? Know that those would be sp2 hybridized because there's only 2 bonded domains around something. Another example. Let's go like this and like this. Okay? 2 total bond domains, sp hybridized. Okay? Remember, count only those bonded domains. Okay? Even though there's a triple bond there. How about this guy? NH3. Okay? 1, 2, 3. Do I count these? Yes, you count the unshared pair of electrons. Therefore, it would be sp3 hybridized. Remember how to count it? S, P, P, P. This stands for S, and those are your 3 P's. And count each one of the domains of electrons where things are at. Okay? How about something like PF5 that we had just a little while ago? Remember 1, 2, 3, 4, 5 fluorines around the phosphorus? Now you got to count it S, P, 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 D. This would be sp3d hybridized. Okay? How about if it's got a multiple bond? Like, well, I had one up here, but let's say it's carbon dioxide like this. sp. This would be sp hybridized because there's only 2 domains of electrons around there. 2 areas of bonding or non-bonding. How about if it's got, other examples up here. How about 6 bonds, like XeF4. This doesn't have 6 bonds, so it's actually really cool. It's going to end up looking like this. Xe1, 2, 3, 4, unshared pair, unshared pair. Remember, count the unshared pairs. S, P, 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 D, D. So that'd be sp3d2. Remember how to count it? Hybrid orbitals. Lastly, if you have multiple bonds. Multiple bonds give rise to sigma and pi bonding. If it's just a single bond, like for instance the phosphorus to the fluorine right here, this is called a sigma bond. If it's a carbon to an oxygen or something to an oxygen or something to something and it has a double bond, one of them is a sigma bond. The other one is a pi bond. Remember, pi bonds are like this, where they come from the unhybridized p orbitals and they have this overlap above and below the internuclear axis, making them a little bit weaker. Other pictures? Right here. Here's CH2O, okay? CH2O. You can see in this picture right here, we've got the orbital overlap between C and O, making a sigma bond. And since it's a double bond right here, we've got this above and below the internuclear axis attraction happening, making the double bond happen. That's a pi bond. And we've got sigma bonds right here. You can remember sigma single, and then anytime there's a double bond or a triple bond, the first bond is a sigma, the rest are pi's. Here's another example right here. 2 pi bonds in this guy, one up here, and then one on the sides. Some people get confused when they see this because they think each lobe of this is a pi bond. No, the above and below is a pi bond, and then the side and the side is a pi bond over here as well. Page 369 in your textbook, lots of good examples. Here they actually label the sp2s and the sp3s. I'm sorry, the sp2s, and then the p bonds, p's in there that would form that pi bond above and below right here. All right, let's look at a couple of examples before we get too far gone with this. Let's look at 2011 Form B. Yep, this was last year, or just a recent year in case you're watching this a different time. 2011 question 6, complete Lewis dot diagram as a molecule given below. Identify the hybridization of the valence electrons around the carbon lane CW. So here's CW right here, and it wants to know the hybridization. We just did this. SP, P, so it would be sp2 hybridized, and lo and behold, yes, that's the answer. Okay? Next, it says estimate the numerical value of the HCO bond angle in the molecule. Okay, here's the HCO right here, HCO. So what they're asking about is what's the bond angle of this guy right here. Notice it's 1, 2, 3, 4 bonded, 0 non-bonded, tetrahedral shape. Bond angle for that, 109 degrees, 109.5, okay? Appropriate explanation, 4 bonded, 0 non-bonded. It's the Vesper theory. Let's see. Ethyl methanoate is synthesized in the laboratory. In the box below, include the Lewis dot diagram, the methanoic acid molecule. They drew the Lewis electron dot structure for it. Notice it's an acid, so it's got an O and an H. It's an oic acid, so it's a C double bond, OH. Hopefully you remember that from the brief organic unit that we did. Next, it says in the box below, draw the Lewis electron dot diagrams of a methanoic acid molecule and a water molecule in an orientation that allows the hydrogen bond to form between them. Now, we haven't reviewed chapter 11 yet with hydrogen bonding, but you should be able to get it. This water molecule is polar. Negative partial charge here, positive partial charge here. Okay, and you can have the methanoate molecule right here, and you can see that there's going to be a negative charge out here on the oxygen, and so then you can have an attraction between the negative and the positive. And right here, you've got the OH with a positive charge right here to the negative water molecule, and then the H with the positive charge here on the H and a negative on the OH right there. Excellent picture, great question. Then they go on and they ask a question about some K stuff from chapter 1. 2010, question 5. Using the information in the tables below, respond to the statements. Questions that follow. Your answers will be in terms of principle of molecular structure and intermolecular forces. Draw the complete Lewis electron dot diagram for ethine, appropriate cell above. So here's ethine C2H2. You should end up with the C triple bond CH here and an H here. Okay? Which of the 4 molecules contains the shortest carbon-to-carbon bond? Well, of course, you should choose the one with the triple bond because, you know, more strong, more bonds, stronger. Lewis electron dot diagram of a molecule of ethanoic acid is given below. Carbon atoms in the molecule are labeled S and Y respectively. Identify the geometric arrangement of bonds. So they want to know this geometric arrangement right here, okay, of this carbon atom X. So I'm going to draw it just a little bit larger here. You can see it goes C to double bond O to another OH right here. So you can count it 1, 2, 3. 3 bonded domains, 0 non-bonded domains, known as trigonal planar. Carbon Y right here has 1, 2, 3, 4 bonds around it. So you could say tetrahedral, 4 bonded, 0 non-bonded. The energy required to boil ethanol. There's energy required to boil ethanol. Consider a statement. Ethanol boils. Energy goes into breaking CC bonds, CH bonds, CO bonds, and COH bonds. Is the statement true or false? Justify your answer. Super trick question. Super trick question. Now they're finding out if you know the difference between breaking these bonds and separating the intermolecular forces between one methanol or ethanol atom and another. All you're doing when you're changing the phase is breaking the intermolecular forces. In this case, it would be hydrogen bonds and London dispersion forces that would be broken. Okay? Keep those straight. You don't break bonds when you change the phase. You don't break bonds when you change the phase. You don't break bonds when you change the phase. Identify a compound from the table above that is nonpolar. Justify your answer. The one that was nonpolar right here were the ones that are completely symmetrical. So ethane would be nonpolar or ethyne would be nonpolar. Either one of those were possible ones. Let's see. Oh, they go on to talk about ethanol being soluble in water. That's a chapter 11 one. And then one is not soluble in water. The ethanol is soluble in water because it can have the hydrogen bonding with the water. That was a really good characteristic. Last one, 2006, question 7. Compounds SEF4 and BF4 react to form an ionic compound according to the equation below. Really nice reaction right there. Draw the Lewis structure for SF3 plus. Notice they put the plus outside here. And notice they just use dots there. They just use dots there. They don't put the dashes. You can put the dashes between the S's and the F's. They just left the dots, I think, because it's easy to print, and that's another possible way. Identify the type of hybridization. So if you look here, it's got 1, 2, 3, 4 bonded. 3 bonded and 1 non-bonded domain. So count them. S, P, P, P. Should say sp3 hybridized right there. Identify the geometry. Well, it's 3 bonded and 1 non-bonded. That's called trigonal pyramidal. See, bang, you got to know the names right there. That's why I love to be the Playboy. Test loss has got to be memorized, because they're going to ask you a cold question like that. It's not on the crappy periodic table. Predict whether FSF bond angle in SF3 cation is larger than, equal to, or smaller than 109.5. Well, you should predict that it's less. It's less because this unshared pair of electrons right here forces these closer together, because remember, an unshared pair of electrons takes up more space than a shared pair of electrons. Let's see. These react to form a compound. Draw the Lewis dot structure for SF5 and CSSF5, the anion in CSSF5. So here it is, sulfur expanded octet with an unshared pair of electrons. Now you've got to count. 1, 2, 3, 4, 5, 6. We've got 5 bonded, 1 non-bonded. Count them all for the hybridization. SPPPDD, SP3D2 hybridization. What's the geometry? You've got to know it cold. Square pyramidal. Okay, square pyramidal. Oxidation number of sulfur. Now you got to go through some chapter 4 stuff and you find out that sulfur's posse 4. Good luck with your Lewis electron dot structures, memorizing shapes, and chapter 4 review, or chapter 8 and 9 review.